Hey, so this is Joe, and this is the 6th video of the 11th chapter of Stewart's Calculus, and we're going to be talking about Taylor and MacLaurin series. So, basically, what a Taylor series is, what the formula for a Taylor series is it's a power series with a coefficient, a special coefficient that makes it so that this kind of series will be able to approximate a value of just about any function. And so when we have the entire series, when we have every single term in sigma notation like this, it actually is a certain function, whatever you choose it to be. And so we are able to find the Taylor expansion for a certain function by using the special definition of the Taylor coefficient, where we get the derivative, and whichever number derivative this is, it depends on n. So, for example, the 0 derivative f0 up here of a, that just corresponds to f of a. And f when n is 1, that's the first derivative of a. And then when n is 2, you'll get the second derivative of a, and so on and so forth, 5th, 6th, 7th. And then the coefficient is over n factorial. And your book kind of goes into a proof for this, but conceptually all you need to know is the way that we're able to approximate this function is since it's a power series and it starts at n equals 0, we're going to get the function itself about a over some constant times x minus a, and then so yeah, let's just write x minus a, or wait, no, because that would be n to the 0, plus, and then a little bit of a change in that function, and then a little more of a change, and then a little more of a change. And so when you add up all those tiny changes, you'll be able to approximate this function for any value of x. And here's a stipulation: any value of x, really what you want to do is make it so that the value that you're trying to approximate is close to a. So say you're trying to figure out the square root of 4.1, and so that comes from the function root x. You wouldn't want to make this about 2, because then you'd need to add up a bunch of little changes, meaning you'd need to use a lot of terms before this series starts to get accurate. Rather, you want the a to be close to what you're trying to approximate. So in this case, you'd want to make a equal to 4. So you wouldn't have to add up too many little changes before you'd start to get a close approximation. And now a MacLaurin series, because so often we want to approximate functions about 0, we call that its own kind of series. That's a MacLaurin series. A MacLaurin series is basically a Taylor series where a equals 0. And so one concern you might have, one more concern, is so if this series starts at n equals 0, what's 0 factorial? Well, we're just going to use the convention in math that some people adopt, that 0 factorial is 1. We're just going to use that. You can read up about why we use that, but that's just, we're going to take that as a convention that we're using. So, first, let's write out, let's do one of these. Let's do the MacLaurin series for the function e of x, e to the x. Alright, so if we're going to write out the MacLaurin expansion for e to the x, first we want to write out our formula. So f of x is going to be equal to the sum, and starting at 0 going up to infinity, of f to the n, and since this is a MacLaurin expansion, it's going to be about 0, n factorial, and again, since it's a MacLaurin expansion, we don't need to write out that minus a, x to the n. So this is the expression that we're using. So first, in order to write out what this particular series is going to be, we need to find a couple terms, probably 3 or 4, to the point where we're going to be able to start seeing a pattern, and then write out the general expression for that series. And so in order to do that, we have to find a couple derivatives. So first we're going to need to find just plain old f of 0, and so e to the 0, that's going to be 1. Now f prime of 0, that you take the derivative of e, e to the x, you still get e to the x, so that's going to be 1. The second derivative is still going to be 1, because remember, the derivative of e to the x is always itself. So it looks like we can safely say that all the derivatives of e to the x at 0 are going to be 1. So that makes this a kind of easy problem to solve. So now let's start finding terms for this, and we're going to call each of the terms a p, and then down here that's going to represent the n, which n we're on for each term. And so it's going to be p of x, because we're still using x, and remember it's all going to be about 0. So we want to find, so the derivative, that's going to be 1 over, and then n is 0, so we're using our convention, 0 factorial is going to be 1. And then this would be x to the 0, so that's a 1, 2. So our first term is 1. So p sub 1 is going to be, we're using our first derivative, so that's going to be 1 over 1 factorial is also 1. So that would be a 1, and then x to the 1 is x. Third term, so when n is 2, the second derivative of x is 1, and 2 factorial is 2, so that's going to be half x to the 2 x squared. And then our third term, or sorry, our fourth term, which is n when n is 3, that's going to be 1. The fourth derivative, what am I talking about? The third derivative is 1. 3 factorial is going to be 3 times 2, which is 6, and this will be x to the third. So now we can kind of see a pattern. So now we can write out our general term, and we can actually then write out f of x is equal to this. And so we see that down in the bottom, this is our denominator is still going to be n factorial. N factorial. We've always got a 1 on top, so we don't need to really write that out. And the x is just going to be x to the n. So that is the MacLaurin expansion for e to the x. And now this is a really important expansion to memorize, because if you ever encounter a function, for example, you could write it g of x is 2e to the x plus 1, or something of that ilk, and we're asked to find the MacLaurin expansion for this, you can replace this, the e to the x, with this expansion, and where the x is right here, add in a plus 1 and multiply all this by 2, and then you'll get the Taylor expansion for this. So this is MacLaurin expansion for this. So that's a really helpful formula to know, especially for the AP, in terms of going fast on the free response and the multiple choice for that matter. And so on the next screen I'm going to show you 4 MacLaurin expansions that are really helpful and you should really just know for the AP, and all of them are proven in your book. We just went over this one, but I'd also check out the proofs for these in your book. But so let's check that out right here. Alright, so here are 4 MacLaurin expansions that are really helpful to commit to memory for the AP. And we've got e to the x, which we just proved, sine x, which we're going to do a problem related to this, and we'll see how that works, but it's this series. We've got cosine of x, and we've got the natural log of 1 plus x. And the important thing to note between these is the first 3 expansions all have an infinite radius of convergence, so they converge for all values of x. However, the MacLaurin expansion for the natural log of 1 plus x is only 1, so be careful of that. Be careful what values you're trying to approximate with this. So really, only use I'd recommend only using values less than 1, or the absolute values of which are less than 1. And the other thing to note is these are all kind of typical power series that start at n equals 0. However, the natural log of 1 plus x starts at n equals 1, which kind of makes sense considering that you can't take the natural log of 0. So those are just some important things to note and some things to commit to memory. So first I'm going to show you how to use one of these MacLaurin expansion formulas to solve another problem to find the MacLaurin expansion for a more complicated function. So we're going to do that right here. Alright, so we're going to do number 48 on page 790, and this actually adds a layer of complexity to what I was just talking about. This question asks us to express this integral as a MacLaurin series. Now, you might be thinking, oh my gosh, that sounds so difficult, but really all we need to do is find a MacLaurin series for this function that's being integrated, and then integrate a couple terms in that function, find a pattern, and express it as a series. So first, all we're going to deal with is finding the MacLaurin expansion for a function f of x is equal to e to the x minus 1 over x. And now that's not going to be terribly complicated because we already have memorized the MacLaurin expansion for e to the x. We know that e to the x is equal to the series n starting at 0, going to infinity, of x to the n over n factorial. So, if we were to expand this out, we could write that e to the x minus 1 over x. We have this equality, why don't we just write that series in the place of e to the x to the n, over n factorial, and then we got the minus 1 and we got the over x. And all this minus 1 and over x mean is that from the entire sum, the infinite sum that's implied by this series, you're dividing each term by x. Well, okay, first you're subtracting 1 from that entire sum, and then you're dividing each term by x. So if we were to write out the first term of the series that expands out this function, it would be 1 over x minus 1. So we would get 1 minus 1 over x, and that would be 0. The second term, when n is 1, we would get x over 1 minus 1 over x. So that would be x minus 1 over x. And we write out our second term, and that would be x squared over 2 minus 1 over x. And then we can simplify that to be x squared minus 2 over 2x. And then we get our fourth term when n is equal to 3, and that will be x cubed over 3 factorial, which is 6, minus 1 over x, and we can rewrite that x cubed minus 6 over 6x. So we kind of can now see a pattern developing here. The x's start to the power of 0 and go up incrementally by 1. They're subtracted by some value that looks to be the factorial of n, and under it is x. There's always an x, that's just a constant, times it seems to be the factorial of n. But remember, and so we could write out that function here as the infinite series of x to the n minus n factorial over n factorial times x. However, this is not the function we're seeking. What we're seeking is actually big F of x, which is the integral of f of x. But isn't it easy to take the integral of a large sum of numbers? You just take the integral of each term then, right? Well, let's write out all these terms in terms of a sum, as the series would imply, take the integral of them, and then start to find a pattern. And that's how we're going to approach this. Alright, so now we've got these equalities. Big F is equal to the integral of e to the x minus 1 over x, which is equal to the integral of the series that we just found earlier. And now, when we take the first 4 terms of that series, this integral is approximately the integral of each of these terms. And hopefully, once we integrate each of these terms, we'll see a pattern emerge. So, first off, we can rewrite each of these terms. And we can basically just by doing some algebra on each of these fractions. So, we're going to get 0 plus 1 minus 1 over x plus 1 over 2x minus 1 over x plus x squared over 6 minus 1 over x and dx. So we do see a pattern. There's a minus 1 over x after every single term. And Yes, there's a minus 1 over x after every single term, so that's a pattern. And it looks like we've always got an x to the something in each denominator, right here, and we've got what looks to be an n, some sort of factorial in the denominator also. And you can pick out the pattern yourself, but it looks like everything's also shifted over to the n plus 1 here, because the first term is 0, right? So this will end up being the series as n starts at 0, between 0 and infinity, of x to the n plus 1, because you see, and we're not counting these 1 over x's as terms. Oh, I'm sorry, we even forgot to integrate. Let's integrate first real quick. But yeah, we're not writing the series for what's inside here. We've already done that. First, we want to find the series of what's being integrated. So let's integrate, and we'll get x minus the natural log of the absolute value of x plus x squared over 4 minus the natural log of the absolute value of x plus x cubed over 18 minus the natural log of the absolute value of x. So we see every other term is minus the natural log of the absolute value of x. So what we need to say is, okay, so every other term, that is what every other term is. So we're going to need to have that only occur at every other term. But otherwise, let's try to take care of the x plus the x squared to the 4 over 4 and all this. And what we'll get, and so we can write that out as one series. Each of these terms, we can think of that as its own series. So these terms we can write out in the series x to the n plus 1 over n plus 1 factorial times n plus 1. And then how do we deal with each of these minus the natural log of x? Well, if you think about it, that's kind of attached to every single term. So we just need to write minus the natural log of the absolute value of x onto this series, and that'll take care of it, because that'll end up being added after every term. And so we start this at n equals 0, infinity, and that is equal to big F of x. And that is how we solve these integral problems with MacLaurin series. So now let's go on and do a slightly different problem. I'm going to do number 20 in your book now, and it asks us to find the Taylor series for the function 1 over x about -3. So let's just remind ourselves of our Taylor series formula. We're going to get f to the n about a, which is going to be -3, over n factorial times x minus a, so that's going to be x plus 3 to the n. So let's start writing out terms here. So our first term, when n is equal to 0, we're going to have to find, we're just going to be using the function, no derivative. So it's just going to be 1 over x, and this n's going to be a 0, so that'll be a 1. This 0 factorial will also be a 1, so we just write out 1 over x for our first term. So when n is 1, for our second term, we have to find the first, we have to find our first derivative here, which is going to be -x to the -2, and n, or 1 factorial, is just going to be 1, so we don't have to write out anything in the denominator, and we will have our x plus 3, then to the power of 1. So now we're going to get our third term, and that's when n is going to be equal to 2, and so we'll get our third derivative, which is going to be x to the -3, and then 2 factorial is just 2, and we'll get an x plus 3 squared. So already we can start kind of seeing a pattern here, and you can kind of identify that pattern, but we can express that pattern in our series, and starting at 0 and going to infinity, as x to the -n plus 1, and it's negative because all the exponents are negative here, and we're adding 1 each time, so n's not going to be multiplied by anything. But it doesn't start at n being 0. There's already an exponent when n is 0, so we have to say n plus 1. And that is all over n factorial. We weren't changing anything in the coefficient, really. And then we've got our x plus 3 to the n. That remains pretty constant. The n corresponds to these n's down here. But the series is alternating. You see we got a positive, a negative, and then presumably a negative later. And it's positive when n is 0, so we'll just have n negative 1 to the n instead of negative 1 to the n plus 1. And this is our Taylor approximation for the function 1 over x about about negative 3. So that's it for Taylor and MacLaurin series. I hope that helped you a little bit. And stay tuned. Actually, I think this is the end of Calc BC, single variable calculus completely. In terms of Stewart's calculus, I'm going to be making videos for Stewart's calculus, differential multivariable calculus, so stay tuned for that. It's actually some pretty exciting stuff as well. So thanks.